Welcome everyone to the last installment of the tutorial seminar series. And today I'm very excited that we've got Yi-Lun Liao, who is a final year PhD student at MIT, advised by Professor Tess Schmidt, here to talk about his work on Equiformer and the dense pre-training techniques that he's developed whilst at MIT. And then we also have Aditi Krishnapriyan, who's a professor at Berkeley, also here to talk about some scaling that work that she's been doing or her and her students have been doing in the neural network interatomic potentials, which certainly at Orbital we've been following very closely. Both of these kind of people and approaches to scaling interatomic potentials are super interesting. And yeah, so we'll have 2 talks of 25 minutes with 5 minutes for questions. We'll do questions in the chat. So if you have a question, put it in the chat. We'll do the questions at the end. Yeah, so Yi-Lun, do you want to kick us off?
Yeah, okay. Let me start my part. Okay, so I think, hello everyone, I'm Yi-Lun, and I'm going to present Equiformer and dense equivariant transformer and self-supervised learning for 3D atomic systems. And this is a joint work with my excellent co-authors, my advisor, Professor Tess Smith, Brendan, and Sama from Fair Meta. And here's the outline of my presentation. So I think, first of all, I will present Equiformer, where we generalize the transformer network architecture to build simple and powerful equivariant networks. And second, I will discuss how we scale one equivariant network-specific dimension, the degree of equivariant representations to develop Equiformer V2, and also how we explore and also explore how it performs on large-scale data sets. Third, I will introduce dense, where we generalize self-supervised learning methods from other domains to 3D atomicity systems, so that we can better leverage atomicity model. So that we can better leverage atomicity data and train better models. And I think below I will mainly focus on some motivation and also intuition. And please refer to individual papers for more technical details. Okay, so I think understanding the interactions of atoms in 3D atomicity systems like forces is fundamental to many applications like materials and drug discovery. But simulating this kind of interaction is very time consuming. For example, running DFT for a 3D atomicity system consisting of an exascale based on top of a catalyst, which would take hours to weeks on supercomputers. So this significant cost will hinder the exploration to the large space 3D atomicity systems. So this kind of motivates using machine learning to accelerate the process. With machine learning, we can simulate this interaction just in fractions of seconds with much fewer resources. And since we are focusing on building machine learning models for 3D atomicity systems, I think let's first take a look at the nature of the data. Regardless of which methods we want to use, I think it is true that physical systems will transform in a specific manner. That is, properties will change in a deterministic way when we choose different coordinates to describe the identical system. So this leads to the idea of equivariance and invariance. So maybe it would be helpful to incorporate this invariance or equivariance into the ML models as some sort of inductive biases. And over the past few years, there have been at least 2 classes of networks that have this built-in 3D related inductive biases. And I think they are equivariant networks and also invariant networks. In parallel, another line of research lies in applying transformers to various domains, such as images in computer vision and also graphs. And those work have demonstrated very widespread success. And this naturally raises the question, like, can we generalize the transformer network design to build simple and powerful equivariant networks? And we explore this question and present equiformer, combining the inductive bias of equivariance with the strengths of transformers. Starting from standard transformers in other domains, we have the following three very simple modifications. The first one is we change the internal feature representation from scalars or vectors of degree 0 to equivariant features consisting of vectors of non-zero degrees. And higher degrees corresponds to higher angular frequency when coordinates are rotated. For example, vectors of degree 1 are something very common, the Euclidean vector, or like the x, y, z coordinates that will rotate the same at the same speed when we rotate the 3D coordinates. And I think in this figure, the left is the original feature representation, and on the right is the equivariant feature in equivariant networks. The red cell is the original scalar, but now here we have additional equivariant vector. For example, like the green vector is the vector of degree 1, and the blue vector is the vector of degree 2. The blue vector will rotate like 2 times faster when we rotate the coordinates. And the second part is we adopt the equivariant operations for these equivariant features. And this mainly consists of 2 parts. The first part is that we replace the original operations in standard transformers with the equivariant counterparts, as shown in the first 3 sub-figures. And the second part is that we introduce an additional operation called tensor products so that we can interact vectors of different degrees. And the third modification we have is equivariant graph attention, where in attention, the message sent from source node S to target node T can be expressed as the product of attention weights A sub TS and value vector V sub TS. Attention weights is in the form of scalars, and value vectors are in the form of equivariant features. And here we add tensor products to both attention weights and value vectors in order to interact different degrees. And we improve upon the standard attention by using nonlinear functions or nonlinear NLPs in both attention weights and value vectors, instead of using the original linear functions such as dot product. Yeah, and I think with these 3 simple modifications, we can turn standard transformers into a powerful equivariant network. And we can see most of the difference lies in the attention part, where we introduce tensor products and also the nonlinear functions for better expressivity. And other parts are just exactly the same, are the same as the original transformer, except that we use the equivariant operations. Although being pretty simple, equiformer improves upon previous invariant and equivariant networks on small scale to mid-scale data sets like ND17 and QMI. We also benchmark equiformer on larger data sets like OS20 as GRE here. And we consider the setting of training with relaxed structured data, where more compute translates to better performance. And equiformer can improve upon GNS plus noisy node from DeepMind and Microsoft and Graphomer from Microsoft, and save about like 2.3 times to 15.5 times training time. And I think I want to mention that subsequent works are built upon prior work, so we can compare the difference to kind of see where the gain comes from. So comparing GNS plus noisy node with equiformer plus noisy node, the gain probably comes from modeling 3D structures with Euclidean vectors, which does achieve equivariance, and also the transformer network architecture. And similarly, comparing Graphomer with equiformer, the gain comes from the additional Euclidean vector and also the proposed nonlinear attention. And I think moreover, we can reduce the training time of Epiformer by at least like 3 times, just with better implementation. So for example, the cool equivariance library released by NVIDIA this Monday, they kind of use specialized CUDA kernels to speed up some common equivariant networks. So I think this is just the beginning of optimizing equivariant networks. And with more efforts, equivariant network can be made more efficient and accessible. So, and because of the very simple design, Epiformer can inherit all the advances from equivariant networks, natural language processing to computer vision. And here we focus on the advance from equivariant networks and build upon ESEN to scale up degrees of equivariant operation, to scale up degrees of equivariant representations and build Epiformer v2. And starting from Epiformer, we have 2 simple changes. We first adopt ESEN convolution to incorporate higher degree representations. And then we propose some architectural improvements so that we can better leverage the power of higher degrees. To begin with, ESEN convolution propose a very elegant way to decompose the tensor products into rotation and SO2 linear operation. This can greatly reduce the computational complexity of tensor products and enables using higher degrees in equivariant networks. So here, the top figure illustrates how the compute is simplified. The leftmost subfigure is the original computation, where we need to perform a 3D matrix multiplication. And in the middle subfigure, they find that if we rotate the inputs, they can make the 3D matrix sparse. So here, only the green row matters. Others are just 0, and we can ignore them. And also with some math derivation, they can reduce the 3D matrix multiplication to the rightmost 2D sparse matrix multiplication. And if we compare the leftmost one and the rightmost one, we can see the number of cells involved in the computation is greatly reduced. So as shown in the bottom figure here, they show that this can save lots of training time and also memory compared to the original tensor product operation implemented in EVMN. So this also demonstrates that the equivariant networks still have lots of room for improvement, and we are yet to unlock their full potential. And after we use ESEN convolution to incorporate higher degree representations, we propose 3 architectural improvements to better leverage the power of higher degrees. First of all, we propose attention renormalization and introduce 1 additional layer normalization shown in the right cell here, And we use the normalization after we project the equivariant feature to scalar. And this additional layer normalization can stabilize the input to the subsequent softmax operation, especially when we use higher degrees. And second, we replace the original K activation shown in the leftmost figure with the separable S2 activation as in the rightmost subfigure. And the motivation is that the separable S2 activation can mix information across all the degrees at the same time, while the information only flows from scalars to vectors of non-zero degrees in K activation. So I think it's just a different choice of activation can mix the information across different degrees to some different extent. And we find that the rightmost one is the most powerful one. Third, following the same design of separable S2 activation, we also have 2 separate paths for scalar feature and equivariant feature consisting of vectors of non-zero degrees. We find that normalizing over all the non-zero degrees together is better than normalizing each degree independently. And we benchmark the performance gain of higher degrees and also the improved architecture of the S3 and 2 million data set. And we show that the improved architecture are necessary to perform better when using higher degrees. And Epiformer v2 also improves speed accuracy trade-off across a wide range of compute budget. And we know that optimization like padding graphs for post-compile can also further speed out these models. And when benchmark on the O20, the whole O20 data set, O20 O+D, Epiformer v2 set state-of-art results on O20 leaderboard when it was released. But higher degrees are not always better and can sometimes lead to overfitting. When trained on just OC-time the STRI dataset, Epiform V2 with higher degrees suffer from overfitting and is not better than Epiform V1. But when we use the setting of noisy node and consider the additional relaxed structure data, Epiform V2 with higher degrees does perform better. So the issue of overfitting can be mitigated with stronger regularization from auxiliary tasks and also data computation. And this also motivates the dense project that I'm going to present later. So based on the experimental result, let's take another look at higher degrees. So Epiform investigate the improved architecture for higher degrees. Higher degrees are theoretically more expressive, but they are not always empirically better. And also they might not be optimal in terms of speed accuracy trade-off, because sometimes we increase the training time by like 2 to 3 times, but just get a few gain in accuracy. So maybe we just need to train smaller model for even longer so that we can have similar accuracy gain, but much faster model. But instead, higher degrees provide another dimension to scale our models. As shown in previous work like EfficientNet, we need to scale multiple dimensions to get better performance gains. So here in this figure, on the y-axis is the ImageNet top-level accuracy. The x-axis is the inference cost in terms of flux. This shows that compound scaling corresponding to the red curve here, where they scale width, depth, into resolution together can boost the accuracy much faster than just scaling a single dimension. So the next project I'm going to present is called Dense, where we explore some self-supervised learning methods here. And we have seen transformer architecture transfer pretty well to hyperbaric networks. This leads to another question like, what are other methods that can transfer well to 3D atomicity systems? And here we focus on training methods in NLP and CV, how these methods can better leverage atomicity data and improve models. And so this motivates us to explore self-supervised learning. And one of the most popular self-supervised learning methods in NLP and CV is training a mask or denoising autoencoder. It enables generalizable representation by learning to reconstruct data. And one example in BERT is called, one example in NLP is called BERT, bidirectional encoder representation from transformers. Here the data is I think it's the leftmost figure. The data is a sentence, and we mask out part of the data, replacing some words with a special token mask. And then we feed the partially masked sentence to transformers, and then ask the model to predict the words that are being masked out. And we can apply this similar idea to images. And as shown in the work of MAE, mask autoencoder, we mask out patches in an image and then predict the pixels in those patches. And we show that we can apply this idea to atomicity data as well. But instead of using masking, we try to add noise to and denoise the 3D coordinates following prior work. And we propose denoising non-equilibrium structure or dense, which generalize transformer-specific BERTs in NLP and MAE in CV to 3D atomicity systems, and extends noisy nodes to all kinds of 3D atomicity structures. Now let's take a deeper look at denoising, where we add noise to obtain noisy structure and then predict the noise, as shown on the top figure. And here we first focus on equilibrium structure, where atoms have near zero forces. The bottom figure shows how we obtain an equilibrium structure. So the surface represents the potential energy surface, with red and blue corresponding to high and low energies. We start from a high energy non-equilibrium structure, denoted as a red point here, and then run relaxation to get a relaxed equilibrium structure, denoted as the blue point S sub EQ here. The equilibrium structure has near zero forces and lies in local energy minimum. And as shown on the bottom right figure, equilibrium structure can be viewed as denoising equilibrium structure can be viewed as first adding noise to obtain the high energy cooperative structure, and then finding the nearest local energy minimum given a high energy structure. And for most of the time, there is always one nearest local energy minimum. So this is a many-to-one mapping, and this level well defined. And for this slide, we show that, if we add different noise, the same process just be repeated. The target will always be the same because there is always one unique nearest local energy minimum. However, denoising non-Euclidean structure is not well defined, but ill-positive. The intuition is that non-Euclidean structure have non-zero forces, and atoms are not confined to local energy minimum and can have more possible positions. So the bottom figure shows the target of denoising is not unique when we denoise a non-Euclidean structure. The three structures denoted by the question mark here can be the target, can be the possible target. The target can be the original non-Euclidean structure, some structure on the relaxation trajectory, or even some other structure far away from this relaxation trajectory. There is no way to specify which structure we should denoise. So we address the ill-positive problem with force encoding. We propose to encode forces of the original structure to uniquely specify the target of denoising, as illustrated in the top figure. And if we look at the bottom figure, the forces of the original structure can be used to distinguish the original structure from others. And with this additional force information, the GNNs can somewhat predict the correct structure instead of any arbitrary structure. And we apply this perspective of force encoding to the original Euclidean structure. And we end up finding denoising Euclidean structure would just be a special case where forces are close to zero and do not need to be encoded. So force encoding enables generalizing denoising to both Euclidean and non-Euclidean structure. And we can train the DANs along with the original task of energy and force prediction to further improve their performance. And we benchmark how DANs improve equiformer on some large-scale data sets. So on OS20 S2EF dataset, equiformer V2 plus DANs improve upon equiformer V2 and also some subsequent models. And we train our OS20 as O plus MD, equiformer V2 plus DANs improve upon state-of-art results when submitted. Know that we can train for longer, from 2 epochs to 8 epochs to get even better results. For OS22, equiformer V2 trained with DANs also set the current state-of-art result. And since the paper of DANs was released, there are additional results on map-bench discovery. And I think, and the results are from the OMAP24 paper by Meta. In their paper, they show that equiformer V2 plus DANs improve previous and concurrent works. And when they pre-train equiformer V2 on OMAP24 dataset, it sets the current state-of-art results on map-bench discovery leaderboard, and also improve upon genome from Google DeFi, medicine from Microsoft, and all from open materials. But I think these work advance the performance through complementary methods, and we can combine all of them to get even better results. So putting all the results together, equiformer V2 plus DANs has set state-of-art results on a wide range of data sets from OS20, OS22, ODAC23, OMAP24. Those are released and maintained by Meta, and also the map-bench discovery as of October 18th this year. But I think importantly, I want to mention that equiformer V2 and DANs are heavily inspired by and also built upon lots of awesome prior work, and there are definitely too many to list here. So I just mentioned some of the most relevant work here. So equiformer V2 is, of course, based on transformers and also tensor field network, 3D CNNs, some of the earliest equivariant networks in literature. And also it is inspired by SE3 transformer, vision transformer, graphformer, some of the pioneering work that applies transformers to different domains. It is also built upon E3NN, NeQuip, SCGN, Allegro, Maze, some of the recent equivariant networks, and also SEN, an unconcrete model that try to scale up the degrees of equivariant representations, and also its subsequent equivariant version, ESEN, where they greatly reduce the computation cost of tensor products. And also, DANS is also inspired by lots of prior work, for example, such as noisy node, where they first proposed the idea of denoising 3D atomic systems. And it is also inspired by self-supervised learning methods in other domains, such as ELMO, BERT, MAE, UL2, and so on. So I think it's pretty exciting to see we can put all of these methods together to advance machine learning for simulating 3D atomic systems. And this is the end of my presentation. Thank you very much for your attention, and I'm happy to take questions.
Great, thanks. Cool. Okay, so if you have questions, then if you write them in the chat, then I'll read them out. See, we've got 2 people with their hands up, but it's just a nice comment from Bharat saying, if I've seen further, it's by standing on the shoulders of giants, and saying that, yeah, Yi-Lun is saying the same thing in the context of ML models, although I think it's fair to say that what Yi-Lun has achieved during his PhD is beyond the expectation of most people's PhD work. So cool. Vladimir is asking, like the idea of the decomposition of the tensor product. Have you thought about TT formats for approaching the same task? I'm not sure what TT means in this scenario. I'm less up to date with the latest in equivariance, but
yeah, I guess let me try to guess the question. I think I guess the question is maybe like, because in the ESN convolution, they have different ways to parameterize the learnable parameters. You can use the SL2 parameterization or tensor product parameterization, and they are the same. I think I tried both. I think the SL2 parameterization is slightly better on larger data sets, because you can imagine that there is no dependency between different end components. So I think that's the reason why it is slightly better for large data sets. But the tensor product parameterization is slightly better on small data sets. But I don't think there's a significant difference there. At least that's my experience. Yeah, I think I'm not sure whether this answers your question, but I think I'm happy to follow up if you have like any thoughts.
nice. Cool. Cool. Arthur is asking, could we just briefly summarize how the dense pre-training works? How can we denoise back to a non-equilibrium state?
Yeah, I think so here is the figure. I go through it quickly just because of the time. So if we look at the figure below here, we have the original non-equilibrium structure, and also it's force stable. And we add noise to the non-equilibrium structure, but we encode the force corresponding to the original structure here. And then we feed this chaotic structure, but with original force as the input. And we use this as input and try to guess what are the noise added here. And so I think this is how we use during training. And the reason we need to use force encoding is just because we need some way to specify what is the original structure. Otherwise, I think I try throwing away the force encoding. There's no gain of using denoising.
Yep. Yeah. So it's almost like a kind of conditional. It's a conditional model given the forces. Can you? Yeah.
Yes.
I think that makes sense. Okay. Cool. I think we'll move on to Aditi's talk now, because we are a little pressed for time. So yeah, it's my pleasure to introduce Aditi, who is an assistant professor at Berkeley. Generally works on kind of AI for science, She's part of the Bear group at Berkeley, and yeah, I'll let her explain what she's talking about today.
Great, yeah, thanks for the introduction, and thanks to Orbital Materials for the invitation. So I'll be talking about and continuing a lot of the discussion on neural network potentials here. And I'll be talking about work primarily with my students, Eric, Sanjeev, and Ishan. So I think Yi-Lun already gave a great introduction to neural network potentials. And just to summarize that overview here, a lot of these molecular and material systems can be described by this underlying potential energy surface. And if you have access to that potential energy surface, this is really the oracle for a lot of downstream applications, from MD simulation to geometry optimization and so on. And these calculations are expensive via quantum mechanics and other methods. And so there's really been a lot of interest. I'm sure this audience is really familiar with this idea of machine learning as a surrogate model for computing the potential energy surface and as a proxy for all of these downstream applications. So another just quick recap here of the standard training procedure for neural network potentials. So I think the current meta so far has really been about, you have these atomic structures. They're labeled with energies and forces, typically from some type of quantum mechanical calculation like density functional theory. You amass a large data set of these calculations. You put it through some type of neural network potential. You predict typically the energies and forces, maybe other properties of the system, and you train the model as usual with backpropagation. So often it's this structure to energy, forces, or other predictions type of mapping task where you use this supervised learning setting to estimate the potential energy surface. And for the architecture itself, in this field in particular, graph neural networks have been fairly popular, which is a bit different from a lot of other fields of ML. So I just want to take a bit of time to contextualize a little bit of what we're seeing going on more generally in the broader field of machine learning. This could be fields like NLP, computer vision, RL, many other fields that make up this broader ML scope. And what we're seeing right now with ML for molecular and materials simulation. And I think at first glance, it's really tempting to think that these are really different areas. But as we've seen how the history of ML has progressed, other fields of ML like NLP and vision also looked a lot like ML for molecules many, many years ago. And they've changed a lot in recent years. And there's been this convergence pattern in recent years. And in the case of these two things, we really have these different modalities where in ML for molecules, at one point we had less data, though this is changing really rapidly for certain types of modalities of data. In broader ML, these fields also had less data at one point, but now they also have a lot more data. Though some fields I think are more comparable. I think robotics is actually a better comparison of what's going on in this ML for science field. And the other thing we've also seen is that in the ML for molecular space, we've been building really strong constraints into these models, like putting these really handcrafted constraints and building them in. And this is often quite inefficient at both training and inference time, but it might also be pretty hard to optimize over. So there's a lot of empirical insight in ML right now. And I think that's a common trend that is also held in many other fields of ML. Whereas in broader ML, the focus has been on putting less constraints and building those into the model, but rather highly optimizing for efficiency at training and inference and learning through efficiency. And on that note, this idea of scaling has also been very popular. It's especially in recent years. And often in the molecular space, the models are rather inefficient to scale. So it's hard to scale them to these large parameter counts to learn better or understand the best way to scale them. Whereas in broader ML, there's been tons of effort on building models to scale well and best really exploit GPU computing, which I think is very, very nuanced. And there's a lot of design choices and algorithms that go into doing this well. And then finally, this last point about historically, the way the field has been is to train a new model each time when you want to study something new. And this is, again, how fields like NLP used to be many years ago. Whereas now in broader ML, we really see this idea of you can gain expressivity through all of this scaling. And so you can really go towards general purpose models for a wider variety of downstream applications and then specialize them later to smaller data sets or smaller problems. And I think one of the things to think about here and pose here, just seeing where ML as a field has been going and where ML for materials and molecules is right now, I don't know if these fields should be so far apart. And I think this is also, I think the general community opinion seems to also be shifting this way because we're starting to really see some convergence between these two different fields. So I do also want to really emphasize that this talk is not about scale is all you need. So I think this is a really simplistic view, and it's really easy to just distill to this very simplistic view. But this is actually, I think, a lot more nuanced to think about and a lot more parts of this to think about. Mainly that we're moving towards a world with more data and more compute. And one thing that I think we should really be thinking about is how do we design and prioritize methods that take the best advantage of this and the fact that we are going towards this future vision. And one trend that we've seen again and again in broader ML fields is that general purpose architectures that exploit computing tend to outperform architectures that build in very domain specific constraints into the architecture, especially in the course of the long run. Really natural example of this is how vision performers don't have this inductive bias of spatial locality versus what we saw in CNNs, and how that's progressed and how the models have done better by actually removing some of these domain-specific constraints. And I think at least there's something here that should also make us think in this field. Are there certain things that we should rethink about the current dominant viewpoints in ML for atomistic simulation? And on that note, the dominant paradigm so far, I think, in this neural network potentials area has really been to incorporate constraints and very handcrafted features into the neural network. So this idea of inductive biases for neural networks has been around for a while. Of course, convolutional neural networks have this inductive bias of translation invariance. GNNs have this inductive bias of permutation invariance. I think, again, coming back to the previous point, where we are seeing that fewer inductive biases actually seems to be winning out in the long run in many other fields of ML. In neural network potentials, one of the most common inductive biases you see is this idea of symmetry and geometry. So if we think that it makes sense that certain molecular systems have certain types of symmetries, should we be trying to think about how they fit into the neural network architecture itself? So, and as an example of this, a really common and popular constraint in these neural network potentials is rotational equivariance. So this is, again, I think this audience is probably very familiar with this. So you have models that have node features that are equivariant to rotation. And this is this nice figure from Maurice Weiler showing equivariance, where you rotate some molecule, you rotate the inputs, you predict the forces, and the outputs should rotate predictably, like the force vectors in this case. And typically these geometric tensors are interacted in the model and trained and defined by this rotation order L. So L is equal to 0. These are invariant features, scalars, L equals 1, vectors, and so on. As you go to higher L, you get higher order tensors. And one thing just to note is that these models are typically very inefficient at training and inference. Even with a lot of recent advances, we've also worked on trying to make some of the operations in these models faster, but I think they're still really far from the advances in efficiency that we see in broader ML. And I think because of that, it's not just an efficiency thing, but it's also how do you improve the expressivity of the model? And maybe these models are actually too constrained in some ways, and that's actually inhibiting certain other properties that we can exploit from how we build neural networks in general. So a lot of this investigation actually started with this plot that we would sometimes see in equivariant neural network papers, specifically in the context of neural network potentials. And this plot essentially shows on the x-axis the number of training examples, and on the y-axis the error. And the idea here is that at L equals 0, you have this blue line over here. But as you go to L equals 1, so you now go from invariance to equivariance and higher order equivariance, this line seems to get steeper, and it seems like the models become better and better as you go to these higher order Ls. But when you take a closer look at this, we noticed that there were a lot of things that actually weren't accounted for and not really looked at closely in some ways. So one thing is that sometimes the neural network parameter counts are not controlled for. And so adding, going to higher order L, or going from L equals 0 to 1 and so on, actually adds a lot more parameters. And that's one potential confounding factor here. The other aspect of this is how you add parameters matters. So we saw that in some cases when parameter count was controlled for, different parameters have very different expressivity, and how you add parameters to the model can really change that expressivity. And finally, these plots often deal with really small amounts of training data. So this sometimes assumes that there's only 10 data points of DFT simulated data. And of course, we're way beyond that data regime at this point. On that note, so we decided to actually look at this a little more closely and do a bit more of a systematic investigation and an ablation study on how to scale these neural network potentials. And for this particular thing, we actually did it with a few more data sets as well. But we picked the Open Catalyst project, so this very large data set of catalysis quantum mechanical calculations. This is, of course, a really specific type of system, catalysts, but I think at very high level, it's useful for checking certain things like scaling and efficiency, and it's useful for thinking about how to use these learned representations for downstream applications. One thing to point out is that this data set is really, really big, and many of the current models, these neural network potentials are quite constrained, and they're very slow to train. And as a result, up until this point, the best models on this data set had to all be trained with industry level compute. So typically trained by Meta, for example, to be able to train long enough to see the best performance, just because a lot of other people, I think, don't have the resources to match that level of training and compute ability. So the experiment that we did here was we looked at the 2 million data set for Open Catalyst. This is a diverse down selection. We looked at the equiformer V2 model that Yi-Lun just talked about to investigate rotational equivariance and this idea of higher order L. And we tested the model on a separate validation set that's supposed to be out of distribution. And immediately, the first thing we noticed was that if you look at these models here, you have this L equals 2 model, which has high force error, and you have the L equals 6 model, which has low force error. And so it seems like higher L means lower error. But then when you look at the parameter counts, the L equals 2 model has 19 million parameters, and the L equals 6 model has 83 million parameters. So higher L is actually adding a lot more parameters. And so the parameter difference between these two is quite large. So we continued on with this ablation study, and we decided to increase the parameters in the model in a couple of different ways. So one is that we added parameters for the graph attention operations, and we also added parameters based on the spherical channels, and that's represented by this red box here. The most immediate thing we noticed by doing this is once you get the different models to about the same parameter counts, the error also ends up being pretty similar between these different orders of L here. And if you do this further, so if you add parameters specifically through attention mechanisms versus specifically through spherical channels, when you do it through the attention mechanisms, things seem to be a bit better, at least measured on this particular metric of force MAE. And we took that even further, just added a lot more parameters through attention. Same thing happens, so this is where the errors really go down even further. And then finally, we also modified the architecture to remove rotational equivariance and just operate only with scalars. And again, that's also very much in the same ballpark. And so what this is basically showing is that once you control for parameter counts, it seems like all of the models actually end up being pretty similar to, for example, the original L=6 model, and they all end up around the same ballpark. So there's a few takeaways that we took from this type of ablation study centered around this idea of gaining expressivity through scaling. And one of those things was, okay, if we add parameters through the attention mechanisms versus the indirect effects of adding parameters through higher order L and the resulting downstream inefficiencies, because of course the models that don't have the rotational equivariance property do run a lot faster. The question we really wanted to ask was, can we improve the model expressivity in better ways, in different ways, that are also going to be fast and efficient and easy to optimize over? And really think about this idea of making it very efficient to scale through parallelization, through advances in GPU kernels, through also just general advances in machine learning as a whole. And this concept also ties into this idea of, well, let's make the neural network as expressive and as optimized as possible and learn as much as possible from the data itself and gain all of the physics knowledge from the data itself. And one point about this is, so I actually really don't like model building. I think we're building way too many models right now, and there are a lot of other problems we should be looking at beyond just model building. But when we make claims like this, we have to show a proof of concept of the ideas. And so we did end up actually building a model, which we call the efficiently scaled attention interatomic potential, or ESCAPE for short. And again, I really want to emphasize and stress that this is much more of a philosophy for thinking about how to build models rather than just thinking about this as one very specific model. Because I think this is more generally a philosophy for thinking about what are the design choices and how do we build models and methods in the future that continue to scale with more computational resources and data, and really account for that factor as we move to this vision of the future in the next 5 years, in the next 10 years. So the general overview of the architecture, so you should see the paper for full details. It has a lot more details on all of the different components. The key point I want to mention with this is that one of the things we did try to think about with this architecture is, let's put fewer domain constraints into the model. So we have these different approaches of the input block. We still have a graph attention block in there, though I'll talk a bit more about a lot of the differences there, and something along those lines, which ends up being fairly key. And we also have a lot of other components of the model, but these are generally fewer domain constraints and let the model learn the complexity from the data. And on that note, I think this is really something to also think about further, that we're trying so many things to get around the data. We're trying so many things in the model, in the algorithms to get around the data itself. But I think in the end, this is really what matters. This is really what we should be thinking about, that we're getting more and more data. How do we take advantage of all of that? So one other point here is that we developed this graph attention block, and this is really the key component of the architecture. Again, you can see the paper for more details about this. So one of the things about this block is that actually here we're actually doing graph attention over neighborhoods rather than nodes themselves. So we do this over this max number of neighborhoods, and we use that as our sequence length. And the way this is designed, so we found that doing attention over the neighborhoods actually seems to be more expressive than doing it over the nodes themselves. And the way this is specifically designed is that it's really highly optimized for GPUs. So we can use memory efficient attention kernels within this framework, which lets us accelerate a lot of the operations that you see here. And again, the common theme of this is really this vision of thinking about how do we develop methods that can be made more efficient as more breakthroughs are made. And we do know that, at least in this field, there's so many people working on making a lot of these operations, a lot of the GPU kernels that are used, so much more efficient, because it affects fields of broader ML. And this is really a principle that we've also been thinking about, that this is really the the lowest baseline for the model. This is like a grassroots initial effort, but I think we can go so much further than this. So the model is we did a lot of evaluations on a lot of different diverse data sets. One thing is that some of these data sets like MD17 and QM9, they're really, really overfit, easy to overfit to at this point, and they've been exhausted. So we tried to look at a larger set of more diverse data sets, and we were doing comparisons with the models themselves. So we didn't account for things like denoising objectives. And so this model ends up being the top on, as you measure it by the very specific metrics that these different data sets use, like energy force predictions or geometry relaxations on these catalyst materials and molecules data sets. And one thing is actually that the eval server on Open Catalyst has been down for a few weeks. So things will be made public once that's back up and once that's fixed. This is one result on Open Catalyst. So this is this really large data set with 170 million training data points, and it's a structure to energy and forces type of prediction task where you have these different systems with surface and absorbent and different elemental configurations. It looks like the dots don't seem to appear for some reason, but what this is supposed to show is that this the bottom part here is supposed to be the pink line showing inference speed over the error and energy MAE. So the escape model here is definitely pretty fast. So the inference speed is, for the small model, is quite high. And as you make the models bigger, the energy, and you increase the parameter counts, the energy goes down. But even our largest model here at 317 million is still actually faster than all of the other previous models like GemNet, ESCN, and Equiformer V2. The paper actually has the dots there. I'm actually not sure why they disappeared. And then one thing is also force MAE is another important factor. So you could say that, okay, well, energies are invariant. How did you do on forces, which are equivariant? But you see the exact same trend there. So the same patterns, that the model is faster, but also as you make it bigger, the force ME goes down accordingly. Even there, the biggest models are still a lot more accurate in terms of force MAE, but also tend to be a lot faster. One thing I also want to point out is that I think in a way, this is actually democratizing a few things, because a lot of these previous models were only trained with industry compute. So this was something at that point that only industry could actually train models and have the compute to do well on this data set. And so we're academics, and we could still iterate and get some good results. And in that way, I think in this field, it's actually a little bit more of a sweet lesson than the stereotypical bitter lesson that you may have heard of, that as you remove constraints and scale models, that ultimately works better than trying to build in knowledge into these models. Efficient models, I think at the end of the day, what we really care about is doing good science. And I think efficient models really enable that in a nice way. This is an example of some of our collaborators at Berkeley in chemistry and LBL. They have this new method to find transition states, which you can add on top of any pre-trained neural network potential, and it leverages the differentiability of the potential. So they wanted to study catalytic transition states, and so they wanted to use a really good model trained on the Open Catalyst data set. And they couldn't use any of the other models because the other models were too slow and not memory efficient enough for them to apply their method on top of the model. So they ended up using our model because it was the only one that was fast and accurate enough to use. And this is just an example where on the left-hand side, the standard approach of doing nudged elastic band calculations has a lot higher energy, and the atoms are flying everywhere, and it's a little crazy. Whereas on the right-hand side, when they used our model and then added their new method on top of that, you get something a lot more sane. And the energy barriers are also a lot lower. And so I think this is also one thing to keep in mind that how do we build models that can actually be used now by practitioners who don't also necessarily have the same level of compute and can actually, and I think optimizing for some of these factors like scaling and efficiency could hopefully enable that further and actually get us to solving some interesting science problems. We also did a rotational equivariance check just to see what would happen after we trained the models. So we took this escape model, we trained it on a bunch of these different data sets, and then after we trained it, we did this check where we have a structure, we predict the forces on the structure, then we took the structure, we rotated it, and we predicted forces on that rotated structure. And then finally, we came back to the original structure and we rotated that original structure, the force predictions on the original structure. So we had these two different scenarios and we computed the cosine similarity between the forces in both of these scenarios. And what we see is that it's higher than 0.999. I think we can basically round it to 1 after we train the model on all of these different data sets like OC20 versus training it on SPICE versus training it on MP-Traj. So this is at least telling us that something is being learned from the data. It's at least correctly predicting the rotations with high accuracy after you train the model on these data sets. Coming back to this point of maybe this is something that we could think about learning from the data itself. Finally, the very last things I'll talk about are going beyond the models themselves. So like I said, I think there are a lot of interesting problems here besides just model building. And one thing to keep in mind is how do practitioners actually use the large models trained on all this data? Because often they might only care about a very specific subset or a very specific problem versus the broader range of problems that are in the training data. One thing we've worked on that front is actually looking forward to taking these very large models and distilling them into these really fast and specialized models. So maybe a practitioner only cares about perovskites. We can distill the large model to specifically tackle that very specific area. And then that's something that can be used for downstream applications. And the nice thing is that these smaller models are going to be a lot faster and much easier to run than large, big models. And this is something that we'll post onto arXiv very soon. One really interesting case study I just want to mention, though, with this study that we did on looking at these distilled models and developing a new method to do this type of distillation is when we looked at taking this model, JMP, this is a backbone of GemNet from Nima Shogi, published earlier this year. And this was trained on a ton of data, and it was doing direct force prediction, which I know a lot of practitioners wouldn't approve of too much, especially for molecular dynamics simulation, because you're potentially losing this nature of a conservative force field. So we took this JMP model, we distilled it into a specialized model. In this case, both the models that we distilled it to also do direct force prediction. And then we also compared to what happens if you have an undistilled model and you train it on a subset of data and it's specialized, but it's only trained from scratch on that data. So the distilled model actually, even though it's a direct force model, it actually doesn't blow up in energy as badly as the undistilled model, which was trained on a very small fraction of the data. One thing is that JMP was trained on a lot more data, and actually seems to be this component of the more data you train on, you do get a little bit closer to this energy conservation point, but none of them are actually truly conserving energy. However, if you take that teacher model with fewer inductive biases, so this is this JMP model trained with direct forces, and you distill it into a model that's trained with gradient-based forces, you conserve energy perfectly. And so you can train it, you can get the best of both worlds because you're training it from distilling to an unconstrained model. And then when you have this small data set that you're distilling to and you do gradient-based predictions, you can still get the nice energy conservation that you want, that you wouldn't have gotten from that larger model. So this, I could point to this meta that these teacher models or the larger models really maybe it makes sense to make them less constrained, especially because it seems like we do have some evidence now that you can learn constraints like rotational equivariance from the data itself. But the distilled students can use that representation, and then they can be trained with more constraints if the user wants. Maybe if you want to deal with a very small data set, maybe, and the downstream application you want to specialize to, maybe you'd prefer to do something like train with energy gradients rather than training with direct forces, as an example. And this is a plot of the force MAE over the change in energy. So the gradient-based force models, again, this is on very small data sets, so I think that's why it shows up more here. They conserve energy perfectly, but when you do the distillation, you get a lot better force error versus if you didn't do that at all. And the very last thing I'll talk about, looks like the video isn't playing. Let's see. Okay.
Oh, hang on, here we go. I think.
Oh, okay, got it. Yeah. So one thing, when you run these ML models, sometimes you see some behavior that seems a little bit odd, like this example of this molecule becoming really unphysical as you run it over time. And this is, of course, concerning because practitioners want to use these models, and how can you trust the reliability of these ML models given this? On this point, another thing we've looked at is really trying to think about targeted training strategies to improve this simulation stability, but also to train it more with just energies and forces. So if we start out with our usual training procedure here, where we train a model on a data set of structures with energies and forces, we train this in a supervised learning style. We have this idea that you can check out in the paper here called stable training, which is based off of defining something, a training procedure that explicitly looks for how unstable you are when you run a bunch of MD simulations when you traverse the potential energy surface. And once you find that there are a lot of instabilities, you can then fix this by training to other types of observables. So you could, instead of training just to energies and forces, you could train to other properties that you might compute after you actually run a simulation. So we run MD simulations and compute observables from that trajectory. And then you can, if you formulate this in a specific differentiable way, so using some concepts from implicit differentiation, you can train the whole thing end to end so that you don't have to backpropagate through all of the simulation steps that you unrolled out when you ran these simulations. And this essentially allows you to correct some of those failure modes and also explore the potential energy surface in a different way beyond just energies and forces. And I would think of this as somewhat of a multimodal training strategy to improve these simulations and also get more accurate simulations when you look at observables that you compute. So this is an example of, we didn't actually train it on this observable of diffusivity, but when you run the MD simulation, you can compute a diffusivity coefficient from that simulation. And before we did our training, so this is when you just use standard supervised learning on the energies and forces, you get fairly high errors and the simulations are not super accurate. But after you apply this multimodal training strategy, you can do a lot better, and your simulations seem more stable, but also you're computing these diffusivity coefficients more accurately. And I think this could be potentially a way to think about bridging gaps between simulation data and experimental data as well, since the observables that you get from running an MD simulation may also be things that you could get experimentally. So the final takeaways I just have here are just that I think there are many ways to be clever with design choices for learning through efficient scaling. I think the field has really focused on very specific areas of how to be clever, so to speak. And I think there are actually a lot of different things to factor in or think about with how you do these design choices. And I think it goes beyond purely just, oh, this is only an engineering problem. I think there's also a lot more nuance beyond that. I mentioned this idea of the bitter lesson, this idea that compute efficient scaling strategies tend to outperform when you handcraft domain constraints into neural networks. But in this field, I actually think in a way, this is like a sweet lesson, because I think a lot of very constrained models are really hard to train unless you have a huge amount of compute. And I think these compute efficient scaling strategies actually might hopefully democratize large scale model training so that a lot more people can actually go and do this, not just people who may, not just a very small number of people who may have access to a lot of compute. The other point I just want to say is that I think this makes it seem like, okay, can we learn atomistic systems? Are they easier to learn? But I think they're actually really, really complex. And I think these predefined symmetries like rotational equivariance are actually very simplistic because that's just one aspect of the overall complexity of these atomistic systems. And so I think from this point of view, the data is what contains the complexity and has the most information, and we should just let the neural network learn as much as possible from the data and make it as expressive as possible to learn from the data, which happens to correlate with these scaling strategies. And finally, I think there's many opportunities beyond just model building. Even though I think there's been focus there, I think there's so much more we can do with looking at how to use models, develop these model agnostic methods on top of models, of course, evaluate the models and optimize towards more comprehensive evaluations, which I think is not mutually exclusive with these other takeaways. And I think there's been now a lot of effort to try to do exactly that. So I think the field is going in a very exciting direction. And finally, I just like to thank the great students that I get to work with, and also some of our different funding sources for these projects. And I'll come back to the final takeaways and happy to take questions.
Great, thanks. Yeah, great. So if people have questions, then please put them in the chat like we did previously. Oh, yeah. Yeah, the recordings from all the seminar series will be shared as individual talk recordings on YouTube after the event. Yeah. I was particularly excited by this seminar series because the combination of these two talks is pretty much our roadmap for some of the new orb models, dense attention architectures, and pre-training on trajectory states is combining these two things is a pretty powerful and fairly obvious direction of travel for some of these molecular force fields. So super exciting, and yeah, great talks, and thanks for joining. Yeah, great.
Great, yeah, thanks a lot. And yeah, definitely feel free to follow up. We actually just made the code public today, but there's a few things we're transitioning with the models. So if you have any questions on that, very happy to answer them as well.
Yeah, awesome. Oh, Marcel has a question. His impression was that constrained models generally outperform. Yeah, Aditi covered that earlier on the talk. Yeah.
Yeah, the question about constrained models generally outperform at small data and small compute. So I think actually what we've seen now is that when you scale the model, it can actually still do pretty well on these data sets, even when they're not super large. And I think maybe one of those reasons could be this point about atomistic systems are really complex and there's a lot more going on than just predefined symmetries. So there could be still more to learn. The other thing though is also, and this is something I know other people have looked at, is this idea of data augmentation. So if you're specifically looking at putting that very specific symmetry in, data augmentation actually also seems to work quite well. And I think the other point is that the small data side, it seems like that's actually really, really, really small data is the transition point with these constrained models, and versus with how well they do on what we've seen as broader data sets. But I think this is something that has a lot of confounding factors when you try to compare models and architectures. And I think the idea of actually distilling into smaller models may also be one way to get around this as well.
Awesome. Okay. Yeah, thanks everyone. Have a good rest of the day. And
Great.
yeah, have the
Thanks,
talks on.
thanks a lot.
Yeah, thanks for joining.